everyone. Today we have a special guest. Every guest is a special, of course. Nick Krekelbergh is a teaching assistant and PhD student. His research focuses on the dynamics of microplastics in soils from a pedological perspective. Nick is also an active member of the knowledge center Viae Caspiae of Eureast platform. Please correct me if I have any pronunciation mistakes. Welcome to the podcast, Nick.
Thank you. I'm very glad to be here.
Today, actually, we are diving into a critical issue that impacts our terrestrial environment, where your research lies on, and also ocean life, and even might impact our health. And I just recently watched one video from New York Times well-being. I will also put the post on the screen as I speak. And in that post, it says that there could be a plastic spoon's worth of plastic in our brains and how it might affect our health. But also, I think the main research direction is trying to reduce the exposure to the microplastics. So anyways, this is one of the most attention-gaining intense study areas, microplastics. So could you start off with a brief microplastics 101 overview for our listeners?
Yes, of course. So microplastics, those are plastic particles that are smaller than 5 millimeters. And they are what you could call hallmark contaminants of the so-called Anthropocene, because they leave even stratigraphic markers in our earth deposits in some cases. They come from a wide range of sources. Some are produced intentionally at small sizes, such as microbeads in cosmetics or in industrial abrasives, while others result from the fragmentation of larger plastic wastes. Although the impact of microplastics in oceans has received the most attention so far, recent studies suggest that soils may actually contain several times more microplastics than marine environments. Estimates range from 4 to even 23 times as much microplastics in terrestrial ecosystems than in marine environments. Now, despite this, soil systems have remained underexplored in microplastic research. The first paper on this matter was actually only published in 2012. It was a paper that consisted of one page, just a general status questionis on the problem of microplastics in soils. It was written by Matthias Rillich, an ecology professor from the Freie Universität Berlin. And it took approximately another 5 years before the first dedicated experiments started to be reported in journals. Now, at Ghent University, at our research group, Soil Fertility and Nutrient Management, we also started to work on microplastics around that time. And in our work, we proposed that the discipline of pedology, so soil science, which includes soil formation, classification, mapping, and the study of physical, chemical, and biological soil properties, offers an ideal framework to better understand the fate and behavior of microplastics in terrestrial environments. As we are soil scientists, we are well placed to perform such research because we do know a couple of things about soil. Now, what are the main topics that we are looking at? First of all, we're looking, of course, at the sources of microplastics in soils. So microplastics enter the soils through both intentional and unintentional pathways. In agricultural contexts, intentional inputs include plastic mulch films, controlled release fertilizers with plastic coatings, and the application of composts and sewage sludge. all of which contain high concentration of microplastics. Irrigation water in regions where irrigation is applied, and especially when it is drawn from wastewater sources, that is another major contributor. Outside of agriculture, tire wear particles from road traffic are also now considered as one of the largest single sources of microplastics. These particles are deposited on roads, picked up by wind and water, and eventually end up in adjacent soils and surface waters. Atmospheric deposition, especially of synthetic fibers, is also increasingly recognized as a global transport factor, allowing microplastics to reach even remote or natural protected nature areas. Now, once in the soil, these microplastics, of course, don't just stay where they are. Their movements can be vertical, down into the profile, or lateral, across the landscape. Vertically, microplastics are redistributed by biological activity like earthworms or plant roots, human disturbance, tillage, harvesting, and even through colloidal transport in water. Their movement is influenced by particle size, shape, and polymer type. For example, fibers behave differently than plastic beads or irregularly shaped plastic fragments. Fibers, so that's elongated plastic fragments, they tend to get trapped more easily and are more likely to form aggregates with soil particles. Horizontally, microplastics are moved by wind, water erosion, overland flow, and such things. Like other soil particles, they accumulate in depressions, in gullies, and in floodplains. In wind-exposed environments or sandy soils, they can be transported over considerable distances, sometimes even hundreds of kilometers. Now, one of the most important aspects where soil scientists come in is soil properties, the fact that soil properties do matter in all of these processes. Key factors are, for instance, texture and porosity. These logically affect infiltration and transport. If you have bigger pores in the soil, macropores, then you will have a situation in which microplastics are easier transported downward. Organic matter content also matters. So microplastics can bind organic particles or they can be incorporated into soil aggregates, which then in turn influences their ability to move downwards in the soil profile. Properties like pH and mineralogy also are important. They affect surface charge of both the soil particles and the microplastics, and this can promote or inhibit movement. And I mentioned aggregates already a couple of times before. So soil structure is effectively a very important feature when it comes to the movement of microplastics. Microplastics are often embedded into larger macro aggregates, and this has, like I said, implications for their mobility, but also for their persistence, because aggregation may shield microplastics, for instance, from microbial degradation. Interestingly, microplastics themselves may influence soil structure also, and bulk density, water retention, even nutrient cycling all those processes or characteristics, properties, they are in turn influenced by the microplastics. So microplastics actually become a soil formation factor. They are not just contaminants as such, but potential soil forming agents, especially over long time scales and, of course, in larger concentrations. And as they are very recalcitrant, these concentrations will only become higher in the foreseeable future. So their influence on soil properties may grow increasingly over time. Now, the research that deals with microplastics has quite a few methodological challenges. There is no agreed upon standards for how to sample, measure, extract, or report microplastics in and from the soils. Also, quite remarkably, most studies only sample the top 30 centimeter of the soil profile, which implies that they miss somehow the vertical variation throughout the whole soil profile, the pedom. Units in which they are reported, they also differ. Some report in items per kilogram, others in milligram per kilogram dry soil, or even in surface area per weight. So this lack of harmonization makes cross comparison of studies difficult and sometimes risks misinterpretation. So we think that sampling strategies should be pedologically informed, meaning that they should take into account things like soil type, landscape position, and also soil horizons. Using soil maps and topographic data may help to improve study design, allow for better predictions, and lead to more accurate contamination assessments. The landscape itself predictably also plays a crucial role in redistributing microplastics. So erosion by water, wind, and tillage can transport microplastics from the uplands to the lowlands, just as they do with soil and organic matter, soil particles and organic matter. Microplastics are light, they often have similar densities to organic matter and behave similarly in some respects under erosion processes. Nowadays, still many assumptions about the movement of microplastics are based upon proximity to pollution sources, but we know that processes of wind erosion and water erosion also play a big part in redistributing these microplastics over the landscape. And for instance, we know that atmospheric transport by wind, can transport these particles over very, very long distances. So, in brief, I think that microplastics are not just a pollution problem in the strict sense, but they are an issue of the whole soil system. So their behavior is governed by the same physical and chemical rules that apply to other soil constituents, and that they should be studied as such. And by embracing a pedological perspective, future research may also become more predictive, harmonized, and ecologically meaningful. And this is important, I think, for advancing our scientific understanding and informing environmental policies, land managers in the face of a rapidly changing planet.
It's interesting that you mentioned that of course, logically, it makes sense that microplastics are given a status of one of the factors influencing the soil formation, or being thought of giving such a status. So, in that sense as well, you recently have been one of the co-authors of the report by OVAM. So, I just used simple Google Translator. Correct me if translation is wrong. It's Public Waste Agency of Flanders. So, congratulations again on this. So, what are the main takeaway messages from this report on microplastics?
Yes, indeed. In the beginning of June 2025, we published a knowledge overview of microplastics in soil, groundwater, and sediments for OVAM, indeed, the Public Waste Management Agency. And I am one of the authors of this report, together with my esteemed colleagues, of course, Lisa Joos, Yin Liu, Bente van Buiten, Josephine de Meulenare, Patria Novita Kusumawardani, and of course the professors Stefan de Neve and Caroline de Tende. In recent years, as I said, the issue of microplastic pollution has attracted growing attention, and soils, groundwater, and sediments have more and more become a cause of concern in terms of microplastic pollution for policy, for government bodies that are responsible for these policies. So that's why OVAM was interested in having such a report. And in this report, we tried to provide a detailed and comprehensive account of the current state of knowledge in this field. Now, what are the key takeaway messages? Well, first and foremost, I think again in this report we state that soil is by far the most important environmental sink for microplastics. And in our study, we showed that 80% of all environmental microplastics are actually found in soils, compared to 12% in water and only 8% in air. So microplastics have been detected in almost every kind of soil, from farmland to forests to urban green spaces, and even in the remote mountain regions and polar environments. And their small size and persistence allows them to travel long distances and remain in the environment for at least decades. The main sources of microplastics in soil are very diverse. Now, the largest contributor is tire wear from road traffic, which accounts for over half of the total emissions. Other significant sources include pre-production plastic pallets, and they are often lost during the handling and the transport of these pallets. Plastic waste, textile fibers, paints and coatings, and a variety of agricultural inputs. I mentioned them already before: compost, sludge, mulch films, and slow release fertilizers. And in Belgium, the port of Antwerp is specifically identified as a hotspot for plastic pellet pollution due to its central role in polymer production and shipping. The concentration of microplastics in soil varies widely across studies and regions. About half of the analyzed samples contain fewer than 1,000 particles per kilogram of soil. But in 12% of the cases, levels exceed 10,000 particles per kilogram. Groundwater is also affected, with concentrations ranging from 0 to 7,000 particles per liter, while sediment studies report levels up to 75 1,000 particles per kilogram of dry weight, especially in areas with industrial activity, also in areas with flooding. Now, the movement of microplastics through the soil is influenced by soil structure, porosity, biological activity, earthworms and plant roots, like I mentioned before, but also weather patterns, such as drying and re-wetting. Now, in terms of ecological and human health effects, the report raises several concerns. Microplastics can change key soil properties such as porosity, bulk density, and water retention, which can lead to reduced soil quality and productivity. Soil organisms such as worms and arthropods can ingest microplastics, resulting in growth and reproduction problems. Plant roots and even leaves can observe small particles, especially nanoplastics, so plastics that are below 100 nanometers in diameter. And this can potentially impair plant health and nutrient uptake. For humans, ingestion is the main exposure route through food, water, and even dust. So inhaling microplastics is actually a very important way of taking them into your body for us humans. So microplastics have now also been detected in human tissues. And apart from this, microplastics can then also act as carriers for harmful chemical additives, many of which are persistent, bioaccumulative, and toxic. And this includes plasticizers, flame retardants, and even PFAS. One of the major challenges in the field of microplastics is that they are extremely difficult to measure, especially at lower end of the size spectrum. There is currently no standardized method for analysis in soils, and the results vary significantly between the labs. And the report reviews a wide range of detection techniques, from FTIR and Raman spectroscopy to dye-based visual methods. And we stress the need for improved quality assurance and avoidance of contamination. In practice, many studies probably underestimate actual microplastic concentrations due to the methodological limitations. What we also explored in the report is possible remediation techniques that are available for removing microplastics from the soil. And these include so-called ex situ methods like pyrolysis, photocatalysis, and magnetic extraction, which are generally limited to the surface layer, and they can be energy intensive or even soil damaging. In situ methods such as phytoremediation using plants or microbial degradation are more sustainable, but they tend to be slow and very difficult to control. So far, there is no silver bullet. Each method has its limitations depending on the soil type, the plastic type, and the environmental context. Now, on the regulatory front, the report that we wrote notes that some action has been taken in marine environments, such as bans on microbeads in cosmetics. But in soils, the regulation of microplastics is still in its so-called infancy. The European Union is taking steps through the Zero Pollution Action Plan and new restrictions on intentionally added microplastics. But most countries lack binding regulations for terrestrial compartments. A global plastics treaty is currently being negotiated with the aim of covering the entire plastic life cycle from production to disposal. Finally, we highlight several research and policy priorities for the years ahead, and that includes developing standardized methods for measuring microplastics in soils and sediments, launching national monitoring campaigns, ideally repeated with sampling every 3 to 5 years, clarifying the role of bioplastics, many of which still degrade into microplastics, expanding research on chemical additives and their interaction with ecosystems, and harmonizing how contamination is reported by particle number or by weight to improve data comparability. Now, we think that Belgium is well placed to take a leadership role in this effort, thanks to existing networks and its strong academic base, and a coordinated European approach supported by initiatives, as there are initiatives like MICOS, like Papillon, and like Minagris, and that will be crucial for developing effective science-based soil policies.
So you mentioned several actually essential points. First of all, we are extremely exposed to microplastics in daily life, even inhaling or from the soil. At the same time, we have tools, no tools to measure microplastic, or the methodology is still under development. It's a pioneering area for research, and that, I guess, is also interesting, because I now want to know more about your current and upcoming research in this area, and if you can share, if you have any key findings from your work, or in what direction are you aiming to do your research?
Well, in my own PhD research, I have done experimental research on and field research on several aspects of microplastic presence in soils. There have been experiments on the distribution of microplastics over soil aggregates and how this evolves over time, so how they get incorporated into the aggregates if you incubate a soil that has been spiked with microplastics over a certain period of time. And also more specifically, the question here is important: what aggregates and what kind of aggregates do they end up in? We also studied the distribution of microplastics in the landscape over a landscape gradient that went from urban areas to more remote areas here in Belgium. Different types of land use, but also in the highly fragmented landscape of Belgium, we try to see what kind of polymers are found and in what quantities are they found when you study them in a gradient that goes from heavily populated city centers to areas where that consists mainly out of forests and heath, which is in Belgium the most natural you can get. We also studied the leaching or the downward transport of microplastics in soils, and for that we used fluorescently labeled microplastics. And I can highlight a few results from one paper that we already published about the work with fluorescently labeled microplastics. It is not on the aspect of downward transport of these fluorescently labeled microplastics in the soil, but on the methodology of detecting them. So in this study, we set out to explore how we could compare two microscopy techniques, Raman microscopy and fluorescence microscopy, to detect very small microplastic particles, and specifically those in the 1 to 2 micrometer range. And we want to see how this worked in soil environments. Now, an important question. This is because the smallest microplastic fractions are suspected to be the most reactive, and potentially they are the most harmful to ecosystems and certainly also to human health. But they are the hardest to detect, particularly in soil where organic matter and complex mineral matrices interfere with the most standard methods unless you use very lengthy extraction procedures. Now, what we did was to introduce fluorescently labeled polystyrene microplasticals in various soil types, from quartz sand to sandy loam, silt loam, and clay loam, and in various concentrations that reflect typically what is to be found in the environment. And we tested the soils both with and without their natural organic matter content, their soil organic matter content. And deliberately, we avoided to use lengthy extraction procedures because we wanted to assess the direct detection capabilities. Now, what we found was quite striking. Fluorescent microscopy clearly outperforms Raman microscopy because it allows to visualize the fluorescent microplastics in all soil types at all concentrations, even in soils that are not treated to remove the soil organic matter, while Raman microscopy is only successful in pure quartz sands and in more realistic soil matrices, so to say, especially those containing soil organic matter or a certain amount of clay. Raman detection actually fails due to the strong background that comes the strong background that comes from fluorescence, and also due to the surface roughness of the soil, and this interferes with the signal clarity. And our study confirms also that when we use samples from a real field experiment where microplastics had been introduced into an agricultural soil to detect their movement, downward transport, we took samples from this field experiments and applied the same methods, and there we found that fluorescent microscopy was incapable of detecting these fluorescent particles that we brought into this soil. Raman microscopy was not effective in doing this. So the takeaway from our study is that for studies involving deliberately introduced fluorescently labeled microplastics, fluorescent microscopy is highly efficient and reliable to monitor their movement. So during such experiments, fluorescent microscopy can avoid time-consuming extraction procedures and deliver rapid results, even at very low particle concentrations. Of course, this does not help us to detect naturally occurring microplastic in environmental soils unless those particles happen to be fluorescent. And of course, typically they aren't. But fluorescence microscopy is a powerful tool for mechanistic research, and it does open new possibilities for tracking the smallest microplastic fractions in the soil, and that has been notoriously hard to do so far. So this is a fluorescence microscope. And we use it to visualize microplastics in soils, fluorescent ones, fluorescently labeled ones. Primitive bright field, just a visual microscope, white field.
So this is
okay, now I remember this one, why sometimes is
This is the Fourier transform infrareds. Our FTIR. And this over here then is our Raman spectroscopy and our Raman spectroscope microscope actually. This is our Raman microscope that's integrated with a visual microscope, so we can operate both in visual mode and in Raman mode. So here we have two lasers, Toptica lasers, and they operate with a laser beam at 732 nanometers wavelength, and that wavelength helps us to separate or rather avoid fluorescence that might interfere with our Raman signal. I will measure the laser power for today. So I put it in Raman mode. Now don't look into the beam, because it might damage your eyes. So what we do in our experiments is we spike our soil with small microplastics that are fluorescently labeled, and we can operate with our Raman microscope in both visual mode as in Raman mode, and we also have fluorescent mode, so we can see by using filters the emission of green fluorescence, the emissions of red fluorescence, and so on. And we spike our soils with fluorescently labeled small microplastics, and then retrace them in our soil samples and then scan the surface of the soil through Raman spectroscopy, perform an area scan, and compare then the results of the area scan to the fluorescent pictures. So by means of creating a so-called heat map, which maps the intensity of certain peaks that correspond to chemical bonds that in their turn correspond to certain polymers. By mapping the intensity of these peaks, we can actually retrace the small particles, which you can see here in the picture in front of me, and then compare their spatial distribution to what we see in the fluorescent picture. And we can get a high degree of correspondence, sometimes maybe a bit less correspondence, because the focal plane from which the fluorescence comes is not always equal to the focal plane from which the Raman scattering is reaching our detector. But in general, we can often retrace the spatial patterns in which the microplastics are distributed on the soil surface of our aliquot sample. And then when we move across the surface of the picture and the heat map, and we can here then pinpoint the particle, and as you can see, there is here a peak, a Raman shift peak around 1000 approximately, and it corresponds to the polymer with which we have spiked this soil. In this case it's polystyrene, and when we make a heat map of this peak, we can see on the most intense spots where this peak is located, concentrated, that these spots correspond to our certain particles. So here we see small polystyrene particles fluorescently labeled. They emit in green, and they are here on the surface of a sand grain, and we see that they are on top of this surface. The sand grain is obviously much bigger than the small particles, who are in the size range of 1 to 2 micron. So here we are going to look at a couple of microplastics, see if we can find them. We extract them from the soil. So here we did a full extraction procedure. We did density separation and oxidation of organic matter, and then filtered this solution. It's not necessary now. So we did density separation to separate our plastics from the mineral matrix, from the soil, and the removal of organic matter through oxidation. Then we filtered the supernatants, and we should have our microplastics here, if there are any, on the filter. It looks like it's going to be a sample with not much on it. Okay, I'll take a more representative one. can contain much, some contain nothing. So our genes can magnify a lot, up to 5,000, but we are quite content with the magnification of 500. And here we do have some microplastics on our filter, as you can see. Need to adjust the focus a bit. But here you can see our microplastics. And we can, if we want to, measure them. So this is a particle of about, well, yeah, it has a bit of a peculiar shape, but let's say it is 71.45 micron in length, if you will. It's a peculiar shape, of course. You can do all sorts of things with this. If it's more spherical, you could measure some kind of diameter. Okay, this one. Voila. So that would be a particle that's like 32 micron in diameter. Of course, it's not a perfect sphere, but it's possible if you have spherical particles like beads.
Now, today I also want to address one of the alarming environmental crises in human history. I think this needs an urgent and immediate reaction, and also to talk in the media mostly. Shrinking of Caspian Sea. It's shrinking at alarming rate due to anthropogenic pressures. So, and to the listeners, Caspian Sea is also a planet's the largest enclosed inland water bodies. So, can you please talk about this issue, because you are also part of the Eureast platform, Viae Caspiae. Please correct me if I have a pronunciation mistake. So
Viae Caspiae, it's Latin language. Yeah, of course, we can also talk about this subject. It is true that I am a member of the Viae Caspiae knowledge platform. I have not done any research on the Caspian Sea, actually, but the Viae Caspiae platform is a knowledge center that is part of the Eureast platform. That's the international platform of Ghent University, focusing on Eastern Europe and Eurasia. And we aim to explore a specific sub-region within the broader area, focusing on one of its defining physical geographic features. So it's not a political or territorial designation in terms of countries or human society. No, we look upon it from a physical geographic perspective. And that's the presence of a sea, the Caspian Sea. And we are not approaching as such the region as a collection of countries or political entities. We emphasize this inland sea paradigm to offer a fresh perspective. And the goal is to move beyond the cliché of the Caspian region as merely an oil producing zone or a passive backdrop of abstract geopolitical narratives. And our key areas of interest include social history, cultural identities, current grassroots dynamics, ecology and the environment, extractive industries and their societal impact, as well as post-oil scenarios and pathways towards economic diversification. We have not set up any research projects from this knowledge center, but we have organized lectures and activities to inform the broader audience about these topics and raise societal awareness. Now, I, of course, do need to stress that I'm not an expert on this topic, but I can tell you a little bit from what I know about it in my experience as a member of the Eureast platform and the Viae Caspiae Knowledge Center. Now, the Caspian Sea, technically, that's not a sea as such, but it's the world's largest enclosed inland body of water. So it's a sort of a massive saline lake with no natural outlet to the oceans. And it's shared by 5 countries, Kazakhstan, Turkmenistan, Iran, Azerbaijan, and Russia. Now, since the 1990s, the Caspian Sea has been steadily shrinking, especially in its shallow northern parts in Kazakhstan. Water levels have already dropped by more than 2 meters, and climate models predict that by the end of this century it could fall by as much as 9 to 18 meters. There are a few key reasons for this. First, of course, climate change. Higher temperatures lead to more evaporation and less rainfall. Second, there is the Volga River. It supplies about 80 to 90% of the sea's inflow, and it is now seeing reduced flow due to upstream damming and heavy water use. And because the Caspian has no natural outlet, any water loss is essentially permanent unless the balance of inflow and evaporation is restored. The consequences are, of course, serious. Coastlines are retreating, ports are being stranded inland, and important wetlands are drying up. And wetlands have served, of course, as vital habitats for migratory birds, for instance. Now, the fishing industry, particularly for sturgeon, which produces, amongst others, caviar, that is also under threat. And then there is a geopolitical side to it. As the water recedes, disputes over maritime borders and access to oil and gas resources are starting to become more complex. Now, it's of course not the first time that the region has seen shrinking of a major water body. In the past, we had the Aral Sea. The Aral Sea is often used as a textbook example of environmental mismanagement. It is located between Kazakhstan and Uzbekistan, and it used to be the 4th largest lake in the world. It was fed by 2 major rivers, the Amudarya and the Sirdarya. But starting in the 1960s, the Soviet Union began to divert these rivers on a massive scale to irrigate the cotton fields in the desert. Now, the consequences have been considerable, if not devastating. Salinity levels spiked. This killed off nearly all aquatic life. Entire fishing communities lost their livelihoods. The exposed seabed became a source of toxic dust storms that carried pesticides and heavy metals into nearby towns. There were serious health problems skyrocketing in the region, from respiratory diseases to cancer and even birth defects. And even the local climate began to change. Winters became colder and summers hotter and drier. Now, at a certain point, there has been a glimmer of hope, because in 2005, Kazakhstan built the Aral Dam with the support of the World Bank, and this dam helped to restore part of the North Aral Sea. Water levels there have begun to rise again. Fish are returning, and small-scale fishing also resumed. But unfortunately, the southern part of the Aral Sea, that is likely lost for good. So in both of these cases, the Caspian and the Aral, these serve as powerful warnings. They show how delicate closed basin water systems um, can be caused irreversible damage due to human decisions, and how it's very difficult, if not impossible, to bring life back once it's gone. So it's about understanding limits and acting before the damage becomes permanent. Now, I would also like to add maybe that the Aral Sea is often seen as proof that the Soviet system caused huge environmental disasters. However, now with the Caspian Sea, we see that the same negative effects are occurring under the current system. And even in the case of the Aral Sea, also negative effects have accelerated in the post-Soviet times with the true nadir during the early 2000s. As such, it is more of a crisis of modernity in general.
From your own perspective, why exactly do you think the EU and Central Asia matter to each other? Because, if you're helping others, it's a zero-sum game. So it's two ways beneficial. So if you could outline this as well.
Well, I think it's of course a reality that we can see that we increasingly live in what they call a multipolar world. So with many, let's say, several power blocks or several so-called civilization states, like Chinese political thinker Zhang Weiwei calls them. But I think that we should not fall into the trap of ever competing power blocks that scramble for power. So I think as people of Central Asia, as people from Europe, but also as people from other parts of the world, that we should actually revive the old idea of fraternity of peoples that exchange knowledge, ideas, and target our resources to improve the life on the one planet that we have in common. And as I said, that goes for the European Union, that goes for Central Asia, but that goes also for all of other emerging geopolitical entities. We are all on the same planet, so we will have to make the best out of it together.
I completely agree. I think that's the sooner we all realize that actually working together, we could have solved our all issues in such a short timing than perhaps overcomplicating it, pointing at each other fingers. And yeah. Anyways, thank you for sharing your perspective and also bringing your research into this discussion. Microplastics, I think it's one of the most essential topics in currently. As well, Caspian Sea is also one of the alarming cases today. Thank you for voicing your opinion, also your perspective on this. I have some general questions, if you don't mind.
No problem.
So, what skills do you believe would be essential to develop as PhD student?
Oh, I think that depends a bit on the kind of research that you are doing. What I would say is it is very important nowadays to be able to work with computers, with computer models, and with technology. So definitely, I would say that in current scientific research, it is important to be able to work with technology and with programming, with different languages for programming, and so on. So that is a very important skill that you need to survive in the current academic environment. But apart from that, I would also say let's not forget about those skills that are important in the research and that deal with the physical world. So let's not forget about field observations, about classical methods of soil description, about classical methods of soil classification, and so on. This knowledge is something that we should not let go to waste. So definitely also let your skills develop in that direction as well.
Any advice for students entering academic world?
Yes, I would say think critically and interdisciplinary. Try to improve your technical skills as well as your wider knowledge, both in your research fields, but also wider knowledge about the world as such. And like I said, technology and modeling are important, but don't forget about empirical observations and the physical world itself.
Thank you.